This lesson will focus on standing waves, which is a special case of the interference of mechanical waves. Alright, so again, standing waves are is basically a property of interference. If you think about it, if you use the simulation on the computer, standing waves are created when an incident wave interferes with a reflected wave. So this is kind of going back to when we talked about the two types of ends in which you can, or two types of boundaries in which you can face. So the first deals with a fixed end, and it also deals with a free end. Okay, and we'll talk more about how these relate to the properties of a standing wave. Okay, but when a wave interacts with a boundary, obviously some of the wave is reflected back, and some of the wave is transmitted. Again, wave is energy, so hopefully that makes sense to you. Okay, so standing waves are produced when a incident wave interferes with a reflected wave, and it interferes in such a way that you get spots of constructive interference, and you also get spots of total destructive interference. Remember, that's where the two waves completely cancel each other out. So what you get is you kind of get a repeating pattern of interference. So it's repeatedly interfere with each other. And what happens is that those waves actually appear to stand still, right? So what you get is a kind of a repeated pattern of a crest to a trough, or really those points of total destructive interference seem to not move. It appears to stand still within the medium. And again, why this occurs is because of interference. So what you should have noticed is that the timing really has to be just right. So the incident wave and the trough, basically what happens is that they have to interfere at the exact same time. So when a wave is introduced into a medium, we'll say in this case it's interfering with a fixed end, right? It's going to reflect back at the opposite phase and come back this way. And what you're going to see is when these waves, when the incident wave and reflected wave interfere with each other, right? This wave interferes with this. You have a crest and a trough. When they interfere completely, you're going to get a spot of total destructive interference. Now, if you introduce a wave at the same time in which they interfere, what you're going to get is that crest, the trough. Okay, and here's your boundary. And this is the point right here where they completely interfere. But now we're introducing a new wave and then the reflected wave, and what happens is just a repeated pattern of introducing the wave that's going to interfere with the reflected wave. And you get, again, these points of constructive and destructive interference, and those represents the standing waves. And this wave appears to stand still in this medium. So the components of the wave is 2 points. There's a nodes and antinodes. All right. Think of nodes, the word nodes, think of it almost as no displacement, okay? No displacement, node, right? Displacement, okay? So really what happens, you get a point where the two waves, the crest and the trough, are going to totally destructively interfere with each other. So they're going to completely cancel each other out. So what you're going to get is a point when those interfere of no displacement. Thus, you get a component called a node. Alright? So that's the point of total destructive interference. And then opposite to that, when they are not interfering, you get points of constructive interference, or points of maximum displacement called antinodes. Okay? So you get points of nodes and antinodes, which is basically just the properties of interference. So on this diagram, the nodes would be all these points here, and the antinodes could be either positive or negative maximum displacement. So those are the nodes and antinodes. Okay, the first type of standing waves we are going to look at are standing waves on a string. And you should have, if not, then you will, look at this in class. What's going to happen is you're going to have some source, right, that's going to oscillate up and down, creating a wave, and a wave is going to interfere with a fixed end. So what you're going to get is you're going to get a standing wave that's going to be created between two nodes. Okay, so the endpoints are going to represent two nodes. Alright, now in the lab you should have noticed that when a standing wave is created, first, again, those waves stand still. The first standing wave you should have noticed was one that looked something like this, right? So a half a wavelength. Alright, you have simply a crest create a crest. That crest is going to travel to this point, right, and then it will interfere. It's going to hit this fixed end, bounce back as a trough, and that trough is going to interfere with the crest at the two endpoints, creating the nodes. So the first standing wave, you have two nodes and one antinode. All right. Notice here that the wavelength of this standing wave would equal 2 times the length of the string. The next standing wave, again, you still have the two endpoints that are nodes, but the next standing wave occurs, now all of a sudden you gain another node within this medium. So you get a crest and a trough, and your standing wave would look something like this. And again, it'll appear to stand still. So here you have 3 nodes and 2 antinodes. And the wavelength of this wave is equal to the length of the string. Okay, so this is the first standing wave. Here's the second standing wave. The third, what's going to happen is we're going to add, just like you've seen before, we go from 2 nodes to 3 nodes. We're going to go to adding one more one more node. Okay, so again, you have the 2 nodes at the end. Now you have 2 nodes within. So you're going to get a crest, trough, crest, and you're going to get the repeating pattern. So you get node, 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 and node, and then you get 3 antinodes. 1, 2, and 3. Okay, and here notice that given this is the length of the string from this point to this point, the wavelength of that the wavelength of the standing wave is this portion right here. So if you look, you have 1, 2, 3 chunks of this wave. 2 out of those 3 chunks represent a wavelength. So our wavelength can be represented by 2/3 of that length. Okay, and this is the third standing wave that we see. And then the last one, you got your 2 nodes again at the endpoints, and you had 1, 2, and now you add in another one. So you get a crest, trough, and it'll appear to stand still like that. So here you have 1, 2, 3, 4, 5 nodes. So node, 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 and node, and you have 4 antinodes. Okay, and if you look at the wavelength of this wave, you have 1, 2, 3, 4 halves of a wave inside that length. Okay, so 2 of those will represent a wavelength. So our wavelength here is 1/2 of the length, and this is the 4th standing wave. So hopefully by now you should be kind of viewing a pattern between these standing waves. We always have 2 nodes at the endpoints, right? The first standing wave, you have 1 antinode. And for every additional standing wave, the second then, you get an additional antinode. And then so on. Now this third standing wave, you get 3 antinodes. The fourth standing wave, you get 4 antinodes. So notice the number of antinodes kind of represents the number of standing, or the order of the standing wave you have. Okay, so we can kind of relate this to a pattern. Alright, so the pattern you should have seen is that with the first standing wave, you get a wavelength of equal to 2L. Second, you get L. Third, you get 2/3 L, and then you get 1/2 L. Alright, so this you can kind of take to a pattern. If we look at the number of, I guess if you want to relate it to the number of antinodes, N can represent the number of antinodes. Alright, so here you get 1 antinode. So N would be equal to 1. So notice here you get, if I take 2L over 1, the wavelength is equal to 2L. Notice here, this is for this one, this is the second standing wave. You get 2 antinodes. If I take 2L over 2, I get a wavelength of L. Here, I had 3 antinodes. I get a wavelength of 2L over 3. Okay, and that's my 2/3 L. And then same thing here, we can look at the fourth one. So we can kind of tie this together and look at kind of the relationship between the wavelength and the number of standing waves. Okay, so the wavelength is related to 2L over N. And kind of taking this information, if we know, okay, the waves are traveling in a string, so they're traveling within the same medium. So we should know that within a medium, the wave's going to travel at the same speed given by the frequency times the wavelength. Okay, so we can also relate this to the speed of the wave and the frequency, where the frequency will equal V over lambda. So the frequency will equal V over 2L divided by N. And this gives us a relationship for the frequency. Frequency is equal to NV over 2L. And here's kind of the expression on how we find the frequency of these standing waves. Okay, so notice that these standing waves occur at specific frequencies. They don't occur at every frequency. It depends on those numbers of nodes and antinodes. So the interference patterns have to happen at a specific frequency. Okay, you increase the frequency, it might be a little chaotic, but at a specific frequency, notice that the wave begins to stand still. Alright, so again, the relationship with that is that the frequency at which a standing wave occurs is equal to N times V. So that's N represents the number, so it could be 1, 2, 3. So the first standing wave, second standing wave, third standing wave. So whatever standing wave equals V times 2L. So it depends on the speed of that medium and the length of that string. And N represents the number of standing wave we have. Okay. Also from the lag, what you should have noticed, or what you will notice, is that let's say we had our first standing wave occurred at 30 hertz, just making up a value. Alright, what you should have noticed is that the second standing wave actually it should have occurred at 60 hertz. So notice that first standing wave was 30, the second standing wave was 60, and then if we went on, the third would be at, not 60, would be at 90 hertz. Okay? So what you notice here is that each standing wave occurs at some integer of what's called the fundamental frequency. So F0 here is known as the fundamental frequency. The fundamental frequency is the first standing wave. Okay? And all other standing waves occur at some integer of this number. So, say I give you a frequency of 60 hertz and I ask you for what is the fifth standing wave. You should be able to quickly tell me, okay, that the fifth standing wave will have a frequency of 300 hertz. Okay, it occurs at some whole integer, some whole multiple of the fundamental frequency. So again, this slide's kind of showing you, given the wave equation, how we came up with that. So again, frequency is related to the velocity or speed of that wave times the wavelength. Again, the speed is constant in that medium. And given the equation that we had, that the wavelength is equal to 2L divided by N, right? We can plug that into this equation, and what we get then is this equation here, which relates the frequency of any standing wave depending on, again, the speed. So it depends on, think of what the speed depends on the medium, and also depends on the length of the string. Alright, so what you should have noticed is that all the standing waves occur at some multiple of the first standing wave, which is known as the fundamental frequency. So we kind of give these standing waves a special name. And for those of you that are in music have probably heard these before, but we call these harmonics. Okay? So any standing wave is known as a harmonic. So take, for example, the first standing wave, which is the fundamental standing wave, the fundamental frequency, is known as the first harmonic. So first standing wave, first harmonic, okay, and so on. So the second standing wave is the second harmonic, third standing wave, the third harmonic. Right, so the harmonic number represents the number of standing waves, so that integer, that N value. So N represents the harmonic value. We can also relate this to something else you might have heard, also known as overtones. Okay, so overtones and harmonics are really the same thing, slightly off. Okay, so overtones are taking into consideration a fundamental frequency. And again, the first standing wave, the first harmonic, represent that fundamental frequency. Okay? Any other frequency beside the fundamental is known as an overtone. So the second harmonic is actually the first overtone. We're looking at, again, the first standing wave does not have any overtone. Now we're looking at the next frequency. That's going to give us our first overtone. Then the third harmonic represents the second overtone. So again, these are basically related to that fundamental frequency. Alright, so we can relate standing waves to the harmonics or overtones, just different ways of stating these. Again, where are these important? They're important in music. In music, and overtones and harmonics, those are something that are important. And that really concludes our lesson on standing waves on strings. The next thing we will look at is standing waves in air columns.